Buckle up, cosmic wanderers, as we soar into the enchanting realm of the habitable zone, the cosmic sweet spot where life might just be waiting to flourish across the stars. Welcome to a captivating journey through the universe's most promising neighborhoods, where we'll uncover the secrets of these Goldilocks regions, not too hot, not too cold, but just right for liquid water and the spark of life. What defines these elusive zones? How do they vary from star to star? And could they harbor alien worlds teeming with mysteries? Get ready for an epic exploration brimming with stellar science, dazzling discoveries, and mind-bending possibilities that will keep you hooked every step of the way. Let's venture into the habitable zone and see where life might thrive in the cosmos. Imagine gazing up at the night sky, a vast canvas dotted with billions of twinkling stars, each one a potential sun nurturing worlds of wonder. But not all stars are created equal when it comes to fostering life. That's where the habitable zone comes in, a concept that has revolutionized our search for extraterrestrial life. Often called the Goldilocks zone, after the fairy tale where everything is just right, the habitable zone is the orbital region around a star where a rocky planet could maintain liquid water on its surface, a key ingredient for life as we know it. Water is the universal solvent, enabling chemical reactions essential for biology, from dissolving nutrients to facilitating cellular processes. Without it in liquid form, life struggles to emerge or sustain itself. This zone isn't a fixed distance, it varies based on the star's size, temperature, and luminosity, creating a dynamic frontier in our quest to find alien worlds. As we dive deeper, you'll see how this concept has evolved from theoretical musings to a cornerstone of modern astrobiology, guiding missions and telescopes in their hunt for habitable havens. Doesn't the idea of cosmic sweet spots scattered across the galaxy make you eager to learn more about what makes them tick? The habitable zone concept has roots stretching back centuries, but it gained scientific traction in the mid-20th century. In 1953, astronomer Harlow Shapley first discussed liquid water belts around stars, emphasizing water's role in life. But it was Michael Hart in 1979 who formalized the continuously habitable zone, modeling how Earth's orbit allows stable water over billions of years. James Casting refined this in the 1990s, incorporating greenhouse effects and atmospheric models to define inner and outer boundaries. The inner edge is where runaway greenhouse warming evaporates oceans, like Venus today, with its scorching 464 degrees Celsius surface and thick CO2 atmosphere. The outer edge is where CO2 condenses, failing to trap heat, leading to global freezing, as perhaps happened on early Mars. For our Sun, a G-type yellow dwarf, the habitable zone spans roughly 0.95 to 1.37 astronomical units. Earth at $1 Australian sits comfortably in the middle. But for hotter F-type stars, the zone shifts outward. For cooler K or M types, it hugs closer. This variability means each star system has its own custom Goldilocks region, tailored by stellar evolution and planetary atmospheres. As stars age, their luminosity changes. The Sun will brighten 10% every billion years, eventually boiling Earth's oceans in about 1 billion years. Isn't it fascinating how these zones aren't static but evolve with their stars, like living entities in the cosmic dance? Let's zoom in on what makes a habitable zone habitable. At its heart is stellar flux, the energy a planet receives from its star, balanced to keep surface temperatures between 0 and 100 degrees Celsius for liquid water. Too much flux, and water vaporizes. too little, and it freezes. But it's not just distance. Planetary factors like atmosphere thickness, greenhouse gases, and albedo, reflectivity, play crucial roles. A thick atmosphere, like Venus, traps heat via the greenhouse effect, where gases like CO2 and water vapor absorb infrared radiation. On Earth, this keeps us warm, but Venus' runaway effect turned it into a pressure cooker. Clouds can cool by reflecting sunlight or warm by trapping heat, a delicate balance. Magnetic fields shield atmospheres from stellar winds, preventing erosion like Mars suffered, losing its air over 4 billion years. Rotation rate matters too. Slow rotators like Venus have extreme day-night differences. Even geology contributes. Plate tectonics recycles CO2, stabilizing climate over eons. These intertwined factors mean the habitable zone is more a guideline than a guarantee, a starting point for where life might take hold. As we explore further, you'll see how these elements create a cosmic recipe for potential biospheres. Our own solar system offers a textbook example of habitable zones in action. The Sun's zone currently embraces Earth perfectly, but Venus sits just inside the inner edge, a cautionary tale of what happens when greenhouse gases run amok. Billions of years ago, Venus may have had oceans and a milder climate, but solar brightening and volcanic outgassing triggered a runaway effect, evaporating water and thickening the atmosphere to 92 times Earth's pressure. Mars, on the outer fringe, once flowed with rivers and lakes, as evidenced by ancient deltas in Jezero crater and minerals like clays that form in water. But its small size meant a cooled core, lost magnetic field, and stripped atmosphere, freezing its water into polar caps and subsurface ice. Jupiter's moon Europa, far outside the zone, defies expectations with a subsurface ocean heated by tidal forces, not sunlight, proof that habitability isn't limited to stellar flux. Enceladus and Titan push boundaries further, with internal heat sustaining liquid environments. This shows habitable zones are star-centric, but planetary ingenuity can create niches beyond them. Could similar hidden oases dot the galaxy, harboring life in unexpected places? Red dwarf stars, or M-dwarfs, making up 75% of the galaxy's stars, challenge our habitable zone concepts. These cool, dim stars have tight zones, often within $0.10, where planets tidally lock, one side eternally facing the star. This could create a terminator zone, a twilight band with moderate temperatures where water might pool. But flares, eruptions 100 times the sun's, bombard these worlds with UV and X-rays, potentially stripping atmospheres or mutating life. Proxima Centauri b, orbiting the nearest star 4.2 light-years away, exemplifies this, Earth-sized in the zone, but its star's activity questions habitability. Models suggest thick atmospheres or magnetic fields could protect, and 2023 JWST observations of similar worlds like LHS 475b showed no atmosphere, but others like GJ 1214b hint at water vapor. Long-lived red dwarfs, trillions of years stable, give life eons to evolve. This abundance, trillions of M-dwarfs, means most habitable planets hug these stars. Isn't it exciting to think the galaxy's life might cluster around these faint red lights? Hotter stars, like F-types, have wider zones but shorter lives, billions, not trillions, of years, limiting evolution time. O and B-type giants, blazing blue, live mere millions of years, too brief for complex life. K-dwarfs, orange and cooler than the Sun, offer a happy medium, stable for tens of billions of years, with zones avoiding extreme flares. Kepler 452b, 1,400 light-years away, orbits a K-star in a zone similar to Earth's, a super-Earth, 60% larger, potentially rocky with stronger gravity. Such worlds could host diverse ecosystems, but higher mass might mean thicker atmospheres or active geology. The star's evolution, brightening over time, shifts the zone outward, dooming inner planets. This dynamic reminds us habitability is temporal, a window that opens and closes. How many worlds are in their prime right now? Exoplanet hunts have exploded our understanding of habitable zones. NASA's Kepler, from 2009 to 2018, used transits, planets-dimming starlight, to find thousands, revealing 1 in 5 Sun-like stars hosts Earth-sized planets in the zone. TESS, since 2018, targets brighter, closer stars, finding TOI 700d, 100 light-years away, in a red dwarf zone. JWST, launched 2021, uses infrared to peer through dust, analyzing atmospheres via transmission spectroscopy, starlight filtered through air, for water, CO2, or methane. 2023 data on K2-18b, 124 light-years away, showed a Hycean world, ocean covered with hydrogen atmosphere, potentially habitable. Biosignatures like dimethyl sulfide, produced by Earth algae, hint at life, though confirmation awaits. Challenges: clouds obscure signals, and geological processes mimic biosignatures. Future telescopes like the Extremely Large Telescope will resolve this. These finds expand the zone's boundaries, including subsurface or exotic habitability. Could a rogue planet, starless but warmed by internal heat, host life? Subsurface oceans redefine habitability. Europa's ocean, 60 to 150 kilometers deep, contains more water than Earth's, with salty composition from rock interactions. Enceladus plumes show pH 9 to 11, organics, and hydrogen for methanogens. Ganymede and Callisto, Jupiter's larger moons, may have layered oceans with fresh and salty water. Pluto's Sputnik Planidia suggests a subsurface ocean, per New Horizons 2015 data. These worlds, outside traditional zones, rely on tidal or radiogenic heat, decay of radioactive elements. Astrobiology now includes ocean worlds, with missions like JUICE to Ganymede in 2034. Life here might be chemosynthetic, like Earth's vent ecosystems, independent of sunlight. This broadens the zone to any world with liquid water, surface or subsurface. Isn't it astonishing how hidden seas multiply life's potential? Atmospheric habitability adds layers. Venus clouds, at 50 kilometers altitude, have Earth-like temperatures and pressures, with 2020 phosphine detection, debated as sulfur, suggesting microbial life in acid droplets. Earth extremophiles like Acidianus survive sulfuric acid, analogues for Venus. Titan's atmosphere, nitrogen-rich with organics, could host methane-based life, where membranes use hydrocarbons. Exoplanets like GJ1214b, a mini-Neptune, might have steamy atmospheres with life in clouds. Biosignatures, ozone, phosphine, guide searches, but false positives from photochemistry complicate. Ariel, launching 2029, will survey 1,000 exoplanet atmospheres. This expands the zone to aerial realms. Could floating cities of microbes dot alien skies? Challenges in defining habitable zones abound. Stellar variability, flares on red dwarfs, can sterilize planets, as models of Proxima b show atmospheric loss over billions of years. Tidal locking creates dayside heat and nightside freeze, but winds or oceans might moderate. Atmospheric escape, from solar wind or impacts, strips water, as on Mars. Greenhouse runaway or snowball states lock planets in extremes. The continuously habitable zone narrows this, requiring stability over billions for evolution. Eccentric orbits, like HD 80606b's comet-like path, swing through the zone, boiling and freezing worlds. These factors remind us habitability is multifaceted, not just orbital. How do we refine the zone for true life potential? The future gleams with promise. JWST's 2025 to 2030 observations will detail exoplanet air, hunting water, and biosignatures. The Nancy Grace Roman Space Telescope, launching 2027, will use microlensing for distant worlds. Plato, ESA's 2026 mission, targets habitable rocky planets. Ground-based extremely large telescope will resolve atmospheres. In our system, Europa Clipper's 2030 flybys and Dragonfly's 2034 Titan arrival will sample for life. If we find microbes, it confirms life's ease, intelligence elsewhere remains open. Astrobiology's horizon expands, from zones to biospheres. What does astrobiology mean for us? It connects our origins to the stars, seeking kin in the void. Your atoms, forged in supernovae, link to this quest. From Miller's flask to JWST's gaze, curiosity propels us. We're astrobiologists at heart, pondering life's reach. As we near the end, let's gaze ahead. Astrobiology, science of life beyond Earth, unveils cosmic possibilities, from Martian microbes to exoplanet biospheres. New missions, data, and dreams will illuminate it. What lives out there? How will discovery change us? The universe beckons, full of wonder. What questions stir your mind? Thank you for joining me on this epic dive into astrobiology, the science of life beyond Earth. I hope your curiosity blazes. If you loved this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about astrobiology? What mystery should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Pioneers. Buckle up, Cosmic Pioneers, as we embark on a thrilling odyssey into astrobiology, the groundbreaking science unraveling the secrets of life beyond our blue planet. Welcome to a mesmerizing journey where we'll explore the origins of life, hunt for hidden oceans on distant moons, and peer into alien atmospheres, all in the quest to answer one of humanity's most profound questions: are we alone in the universe? What clues hide in the icy depths of Europa or the hazy skies of Titan? How are we sniffing out signs of life on worlds light years away? And what might alien life look like if we find it? Get ready for an epic adventure packed with cutting-edge discoveries and mind-bending possibilities that will keep you hooked from start to finish. Let's dive into the captivating world of astrobiology together. Imagine standing on the shore of an ancient Earth, billions of years ago, as lightning crackles across a stormy sky and volcanic vents bubble with primordial chemistry. From this chaotic cradle, life emerged, a single spark that evolved into the incredible diversity we see today, from microscopic bacteria to towering redwoods and intelligent humans. Astrobiology is the interdisciplinary science that seeks to understand how life began here and whether it could exist elsewhere in the cosmos. It blends biology, chemistry, physics, geology, and astronomy to probe the potential for life beyond Earth, from microbial organisms in subsurface oceans to advanced civilizations broadcasting signals across the stars. This field isn't just about finding aliens, it's about comprehending the conditions that make life possible, the resilience of living systems, and our place in the grand tapestry of the universe. As we venture deeper, you'll discover how astrobiology is rewriting our story, one cosmic clue at a time. Doesn't that make you wonder what secrets the stars are hiding? The roots of astrobiology stretch back to ancient times, when philosophers like Epicurus and Lucretius speculated about multiple worlds teeming with life. But the modern field took shape in the 20th century, fueled by advances in space exploration and biology. In 1953, Stanley Miller and Harold Urey's famous experiment simulated Earth's early atmosphere, zapping a mix of methane, ammonia, hydrogen, and water with electricity to produce amino acids, the building blocks of proteins. This sparked the idea that life's chemistry could arise naturally, not just on Earth but anywhere with similar conditions. NASA formalized astrobiology in 1995, establishing the Astrobiology Institute to coordinate research. Today, astrobiology encompasses everything from studying extremophiles, organisms thriving in Earth's harshest environments, to analyzing exoplanet atmospheres with telescopes like the James Webb Space Telescope. It's a field that's grown exponentially, with missions probing our solar system and beyond, all driven by the tantalizing possibility that life is not an earthly anomaly but a cosmic commonplace. At its core, astrobiology asks three big questions: how does life begin and evolve? Does life exist elsewhere in the universe? And how can we detect it? To tackle the first, scientists study abiogenesis, the transition from non-living chemistry to self-replicating life. On Earth, this likely happened around 3.8 to 4 billion years ago, soon after the planet cooled from its molten birth. Theories abound. The primordial soup hypothesis suggests organic molecules formed in shallow ponds or oceans, energized by lightning or UV light. The hydrothermal vent theory, championed by researchers like Nick Lane, proposes that life started at deep-sea vents, where hot, mineral-rich water meets cold ocean, creating chemical gradients that power early metabolism. Alkaline vents, with their porous rock structures, could have acted as natural cell membranes, concentrating molecules for reactions. RNA world hypothesis posits that RNA, capable of storing information and catalyzing reactions, was life's first molecule, evolving before DNA and proteins. Experiments like those at the Scripps Institution have synthesized RNA precursors under vent-like conditions, bolstering this idea. Panspermia adds a twist: life or its precursors might have arrived on meteorites, as evidenced by amino acids in the Murchison meteorite, which fell in 1969 and contains over 100 organic compounds. If abiogenesis is common, life could spark on any world with water, energy, and organics. But if rare, Earth might be a lonely outpost. What if the key to life's recipe is universal? The search for life starts in our solar system, a laboratory of diverse worlds. Mars, our rusty neighbor, tops the list with its ancient water-carved valleys, like Valles Marineris, and sediment layers in craters like Gale, explored by Curiosity since 2012. Perseverance, landing in Jezero crater in 2021, has collected over 20 rock samples, including from a dried river delta, for the Mars Sample Return mission, planned for the 2030s. These could hold fossilized microbes or organic molecules. Methane plumes, varying seasonally and detected by Curiosity and orbiters like Trace Gas Orbiter, INTRIGUE. On Earth, methane comes from geology or biology, but Mars' source remains debated. Subsurface briny water, stable at low temperatures, could host extremophiles, as suggested by radar data from Mars Express in 2018 showing liquid lakes under the South Pole. Radiation and perchlorates make the surface hostile, but underground refuges might preserve life from Mars' wetter past, 3 to 4 billion years ago. The Tianwen-1 rover and ExoMars mission continue the hunt, analyzing soil and air for biosignatures. Could a Martian microbe rewrite our history? Jupiter's moon Europa is another prime target, with its smooth ice shell hiding a global ocean of salty water, estimated at 100 kilometers deep, more than twice Earth's ocean volume. Galileo's 1990s flybys detected a magnetic field induced by saltwater, and Hubble spotted water plumes in 2016, erupting from cracks like geysers. These plumes, containing salts and organics, offer a way to sample the ocean without drilling. Tidal heating from Jupiter's gravity flexes Europa, keeping the ocean liquid and powering potential hydrothermal vents on the seafloor, similar to Earth's black smokers where life thrives without sunlight, fueled by chemical energy. Europa Clipper, launching in October 2024 and arriving in 2030, will make 49 flybys, using radar to map the ice and ocean, spectrometers to analyze plumes, and instruments to hunt for organics. If vents exist, they could host chemosynthetic bacteria, a parallel biosphere. Radiation from Jupiter's belts bombards the surface, but the ocean's depth shields it. Preparations for Clipper and ground-based observations build excitement. Imagine finding life in Europa's hidden sea. What would it teach us about life's universality? Saturn's Enceladus is equally enticing, with its South Pole geysers spewing water, ice, salts, and organics hundreds of kilometers into space. Cassini's 2005 to 2017 mission flew through these plumes, detecting hydrogen gas, a potential energy source for microbes, and complex hydrocarbons like propane. The ocean, 30 to 40 kilometers deep under 20 kilometers of ice, is kept warm by tidal friction, with rocky core vents possibly providing minerals for life. Silica nanoparticles in the plumes suggest hydrothermal activity at over 90 degrees Celsius, ideal for thermophiles. Proposals like Enceladus Life Finder aim to sample plumes for biosignatures, amino acids, lipids, or chiral molecules favoring left-handedness like Earth's life. Post-Cassini analyses and Dragonfly's Titan focus keep Enceladus in view. Could these geysers hold the key to Saturnian life? Titan, Saturn's largest moon, offers a different allure with its thick nitrogen atmosphere and surface lakes of methane and ethane, the only stable liquids besides Earth's water. Cassini-Huygens' 2005 landing revealed dunes of organics, rivers carving valleys, and a prebiotic soup rich in tholins, complex hydrocarbons formed by UV light. Titan's -179 degrees Celsius surface is cold, but subsurface oceans of water ammonia could host life using methane as a solvent, a hypothetical, methanogen, biology where cell membranes adapt to hydrocarbons. Dragonfly, launching in 2028 and arriving in 2034, will hop across Titan's terrain, analyzing chemistry for life precursors. Mission prep and lab simulations advance our understanding. Titan challenges our water-centric view. What if life swims in hydrocarbon seas? Venus, our hellish twin, surprises with potential. Once possibly habitable with oceans, Venus now boils at 464 degrees Celsius under 92 atmospheres of CO2. But 2020's phosphine detection in clouds, a potential biosignature, though debated as sulfur dioxide, revived interest. Clouds at 50 to 60 kilometers altitude have Earth-like temperatures and pressures, with sulfuric acid droplets that Earth extremophiles might tolerate. Missions like Da Vinci, launching 2029, will probe the atmosphere, and Veritas will map the surface. Reanalysis of Pioneer and Venera data fuels debate. Could floating microbes survive Venus skies? Beyond our system, exoplanets expand the search. Kepler's transit method, dimming starlight as planets cross, found thousands, with TESS continuing the hunt for nearby worlds. Habitable candidates like Teegarden b, in a red dwarf zone 12 light-years away, or LHS 1140b, a super-Earth with potential water, excite. JWST's infrared capabilities analyze atmospheres via transmission spectroscopy, starlight filtered through air, for water, CO2, or methane. Data on K2-18b, a Hycean world with hydrogen envelope, showed dimethyl sulfide, a algal byproduct, though unconfirmed. Biosignatures like oxygen with methane suggest life, as they react without replenishment. Challenges. Clouds obscure, and geology mimics. Ariel, launching 2029, will survey 1,000. These finds push astrobiology's frontiers. SETI complements, listening for intelligence. From Drake's 1960 OSMA to Breakthrough Listen's Million Star Survey, we seek radio or laser signals. The water hole frequency, 1420 to 1660 MHz, is quiet for noise, ideal for contact. Technosignatures like Dyson swarms with dim stars, searched in Kepler data. No luck, but the square kilometer array will boost. The Fermi paradox looms. Where are they? Rare intelligence or self-destruction? SETI's optimism endures. Challenges abound. Biosignatures mimic geology, Venus phosphine debate shows this. Distances limit probes, Voyager's 45 years reached interstellar space, but Alpha Centauri is 4 light-years away. Contamination risks forward and back, protecting alien ecosystems or false positives. Funding and politics slow missions. Yet, astrobiology thrives, with NASA's update and conferences like a GradCon advancing collaboration. The future gleams. Europa Clipper's 2030 arrival, Dragonfly's Titan hops, Mars sample returns analyses. JWST's Exoplanet Spectra, aerial survey. Private ventures like Breakthrough Starshot's LightSail probes to Proxima. Biosignature databases refine searches. If we find life, it transforms biology, philosophy, religion, proof we're not alone. What does astrobiology mean for us? It connects our origins to the stars, seeking kin in the void. Your atoms, forged in supernovae, link to this quest. From Miller's flask to JWST's gaze, curiosity propels us. We're astrobiologists at heart, pondering life's reach. As we near the end, let's gaze ahead. Astrobiology, science of life beyond Earth, unveils cosmic possibilities, from Martian microbes to exoplanet biospheres. New missions, data, and dreams will illuminate it. What lives out there? How will discovery change us? The universe beckons, full of wonder. What questions stir your mind? Thank you for joining me on this epic dive into astrobiology, the science of life beyond Earth. I hope your curiosity blazes. If you loved this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about astrobiology? What mysteries should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Pioneers.